Hi, I'm Kathy. In this lesson we're going to look at the graphs of several different equations. Let's start with one called the square root function. The square root function is the function y equal x squared. And what I've got here is a table of values that satisfy this function. When x is 0, y is that squared, which is 0. When x is 1, 1 squared is 1. When x is negative 1, negative 1 squared is 1. 2 goes with 4, and negative 2 with 4. Now what I'm going to do is plot these ordered pairs. I have 0, 0, positive 1, positive 1, negative 1, positive 1, positive 2, 4, and negative 2, 4, and connect these and get a graph of the square function. Now the domain of this function, notice, is negative infinity to positive infinity, extends in both directions to infinity. The range is from 0 to positive infinity, including 0. We call this particular function a parabola. Let's try another. The square root function has equation y equals square root x. And again, we're going to plot some points. Notice that when x is 0, y is the square root of that, which is 0. When x is 1, y is the square root of 1, which is 1. When x is 4, y is the square root of 4, which is 2. And when x is 9, y is the square root of 9, which is 3. And we'll plot some of these points. 0, 0, 1, 1, 4, 2. Here's 9, 3. And we draw a curve through those to get a graph of the square root function. As far as this function's domain and range, notice that from left to right begins at 0 and goes to infinity. We say the domain is 0 to infinity, including 0. The same is true of the range. It goes from 0 to infinity, including 0. I'd like you to try one of these. Here's what I want you to do. I want you to graph x equal y squared and state the domain and range of this relation. Determine whether this relation is a function using what you know about functions. And I've given you part of a table to use, including in the table the y coordinates, and I want you to find the x's and then draw a graph. Pause the video while you work this problem and then restart it when you're ready to check your work. Well, let's see how you did. First of all, filling out the table. If y is 0 and x is that squared, x is 0. If y is 1, x is going to be 1 squared. If y is negative 1, x is going to be negative 1 squared, which is also 1. If y is 2, x is going to be 2 squared. And if y is negative 2, x is going to be that squared, which is also 4. So now we need to plot some points. I have 0, 0, positive 1, positive 1, positive 1, negative 1. Then I have 4, 2, and 4, negative 2. And I'm ready to draw a graph. So I draw a curve connecting those points. The domain of this particular relation is from 0 to infinity. The interval, including 0 to infinity. The range of the relation is negative infinity to positive infinity. So the range as an interval is negative infinity to positive infinity. The relation is not a function. It does not pass the vertical line test. A vertical line somewhere will intersect the graph at more than one point. Let's continue by looking at the graph of the cube root function. The cube root function has equation y equal the cube root of x. And so again we have a table of ordered pairs to use. Notice that if x is negative 8, y is the cube root of that which is negative 2. If x is negative 1, y is the cube root of that which is negative 1, and so on. So we want to plot these ordered pairs. Now to appropriately use the grid we have, let's consider each grid square 2 units. So for example, this one is negative 2. Then the next one's negative 4, and negative 6, and negative 8 in all directions. So we'll plot the point negative 8, negative 2, negative 1, which cuts through half of that particular square, 0, 0, 1, 1, and 8, 2. Now connecting those few ordered pairs, we end up with a graph of the cube root function. It should be a nice smooth curve running through the few points that I've plotted. Its domain, notice if it continues to the left and right, is negative infinity to infinity, and its range is also negative infinity to infinity. Let's move on to another function called a semicircle. The graph of x squared plus y squared equals r squared, where r is greater than 0, is a circle centered at the origin with radius r. Now if you take this equation and solve it for y, it gives the following equations for the graph of a semicircle. Either y equals square root of r squared minus x squared, or y equal negative square root of r squared minus x squared. This is the top semicircle, or half a circle, with radius r, or the bottom semicircle. One other thing to note about semicircles is the graphs of semicircles pass the vertical line test, and therefore they are functions. Let's graph one. Here's what we want to do. We want to sketch the graph of y equals square root of 1 minus x squared and state the domain and range of the function. It is a semicircle, so it is a function. Well, let's take this equation and square both sides and add x squared, and see that our equation came from the circle with radius 1, center at the origin. But since we have a positive square root, we have the top half of this circle with radius 1. So it's going to hit the x-axis at negative 1 and positive 1, and the y-axis at positive 1, and we draw our semicircle accordingly. Now the domain of this is from negative 1 to positive 1. In interval notation we'll use brackets because we want to include negative 1 and 1. The range of our semicircle is from 0 to infinity, excuse me, I said infinity, to 1, not infinity, including 0 and 1. So we use brackets on that interval. Let's continue by looking at the absolute value function. The absolute value function is written y equal absolute value of x. And again, I have some ordered pairs that satisfy that function. Notice that each x corresponds to its absolute value, or y is the absolute value of whatever x happens to be. So if x is negative 1, y is the absolute value of that which is 1. Well, let's plot these ordered pairs. I have 0, 0, 1, 1, negative 1, 1, 2, 2, negative 2, 2, and 3, 3, negative 3, 3. And I connect these pieces, and this graph continues, and that's the graph of the absolute value function. It's V-shaped. The domain of it is from negative infinity to positive infinity. Its range is from 0 to infinity, including 0. Let's continue, but this time we're going to look at a function made up of two pieces of functions we've already seen. So it's called a piecewise function. Here's what we want to do. We want to sketch the graph and state the domain and range of the function made up of the pieces, or the piecewise function, square root x plus 2 for x between negative 2 and 2, and 4 minus x for x greater than 2. One way to come up with this graph is to look at a table of values for each piece. So let's start with the top piece and make a table of values for x and square root x plus 2. The x's we're allowed to use in this piece are between negative 2 and 2. So just arbitrarily picking some, let's use negative 2, negative 1, and maybe positive 2. If x is negative 2, we find the square root of negative 2 plus 2, which is 0, and the square root of 0 is 0. If x is -1, this is the square root of -1 plus 2, or the square root of 1, which is 1. If x is 2, this is the square root of 4, which is 2. So plotting that set of ordered pairs, I have the points -2, 0, -1, +1, and +2, +2. And so a piece of my piecewise function looks like that. Now there's another piece. There's 4 minus x for x greater than 2. So let's see how that piece of the function will look by making a set of values that'll work. Let's pick things greater than 2 for x, like 3, 4, and 5. If x is 3, 4 minus 3 is 1. If x is 4, 4 minus 4 is 0. If x is 5, 4 minus 5 is -1. But another point we have to consider is what happens if x could be 2. It's not allowed to be 2, but it's going to get close to 2. If x were allowed to be 2 in this function, this would be 4 minus 2, which is 2, which would be right on top of the point from the other piece of the function. So keep that in mind. In addition to that, I have the point +3, +1, +4, 0, and 5, -1. So the second piece of the function connects up with the first piece only because if x could be 2, this would be 2. And so I have graphed, and I should say that this piece extends, but not the left. But I've graphed that piecewise function. Let's look at a particular piecewise function. This one's called the greatest integer function. The notation for the greatest integer function is y equal to these symbols enclosing x. And this set of symbols is defined to be the largest integer that is less than or equal to x. Sometimes you can think of the greatest integer function as whatever number x is dropping back to the next closest integer, or to the left to the next closest integer. Let's look at its graph. The graph of f of x equal the greatest integer of x is this set of steps. Notice that each step has a closed dot on the left and an open circle on the right. So if we take one arbitrary step and consider it for a moment, what this means is any x value between -1 and 0 is graphed as -1, which is the y value. Except when you get to 0, you plot the point 0. For example, if I were to put -1/2 for x to evaluate the greatest integer less than or equal to -1/2, I drop back, or to the left, to the number -1. Let's try this out with an example. What we want to do is sketch the graph of f of x equal the greatest integer less than or equal to x plus 2, but only for x's between 0 and 4. And then we're going to state the domain and range. Well, let's consider a few pieces. For example, 0. The greatest integer less than or equal to 0 is 0. If I add 2 to that, I'm at the point 2. Now here's the integer 1, but let's consider 1/2. If x is 1/2, the greatest integer less than or equal to that is 0, and then I add 2. And what that indicates to me is all the way up until I get to the number 1, I will be graphing the integer 2. Well, what about at the number 1? If I put 1 in there, the greatest integer less than or equal to 1 is 1 itself, plus 2 is 3. And what I'm going to get, if I continue this a little bit further, is a series of steps, but I want to stop where x is 4. So I've graphed from 0 to 1, 1 to 2. I'm going to graph from 2 to 3, and one more step, which will be from 3 up until 4, but not including 4. And so that set of 4 steps is the graph of this variation on the greatest integer function from 0 to 4. Now, as far as the domain and range, the domain is all the x's that I was able to plot. And so the domain is exactly the interval from 0 to 4, but not including 4. The range is a little bit more restricted, though, because the range only contains 4 values. It contains 2, 3, 4, and 5. And so we would list the range as those numbers. Let's continue by talking about one more concept that has to do with the graphs of functions. The concept is the concept of increasing, decreasing, and constant. Here's an example to illustrate. What we want to do here is identify any intervals on which the function shown in the picture, in the graph, is increasing, decreasing, or constant. Now, a function is increasing if, in general, it rises as we move from left to right, decreasing if it falls from left to right, constant if it remains the same. This particular function is increasing from negative infinity to the x value 0, so it's increasing on the interval negative infinity to 0, and then it is decreasing, decreasing from 0 to positive infinity. It has no intervals over which it's constant. Let's try another example. Identify any intervals on which the function is increasing, decreasing, or constant. Again, let me emphasize, even though you see an arrowhead here that appears to be pointing to the left, you read a function from left to right as you read words in a book. So this function is increasing from negative infinity to the x value negative 2. So it's increasing from negative infinity to negative 2. And then it's constant from negative 2 to positive 2. Constant on the interval negative 2 to 2. It has no intervals over which it is decreasing. Well, in this lesson we've looked at a number of different functions as well.